Chapter 2: Tables and Graphic Displays of Data. Summarizing data in distribution tables and graphs. Data sets may contain millions of numbers. We need to condense that data into interpretable summaries, and the two ways of doing that are by tables and graphic displays of data. The tables summarize large amounts of data into summary measures like the total or an average, minimum or maximum. Those summary measures used in the tables are created in such a way that all the pertinent information is retained. Tables utilize rows and columns to organize the summary data. An observation is a measurement or score for an individual, typically as the result of an experiment or a study. A frequency distribution contains each unique observed value and the frequency of its occurrence. Consider the years in school data. Several student customers were asked what year in school they were. This table represents the results of that survey. Those who responded were either in their first year, second year, third year, fourth, fifth, sixth, or seventh. The frequency or number of male customers in each of those categories is listed here. Although the table does not include every single observation of raw data individually, it lists them summarized in frequencies. So, for example, this 25 here represents the fact that we had 25 male customers who were in their first year of school. Now, we could have listed all 25 of those individuals out separately, but by summarizing them here, we can include them all in one line, and we have not lost any information. Next, we'll look at a relative frequency distribution, which is very similar to a frequency distribution, but with relative frequencies. And the relative frequencies are proportions, essentially, of the number of times each observed value occurs. So again, here in the first two columns we have the unique values, and in the second column we have the frequencies. The relative frequencies are computed by taking the frequency and dividing by the total, which in this case we had 122 male customers that were surveyed, and so the grand total for the male customers is 122. So if we divide each of these frequencies by 122, that will give us the relative frequency, or the frequency relative to the total. From this we can see that 20%, or a proportion of 0.20, of the male customers are in their first year of school. And looking at these relative frequencies, we can get a better understanding as to the distribution of the years in school for these male customers. So we can see that there are higher values here at the low end than there are at the high end, because we have the numbers like 0.2, 0.2, 0.3, and down here we just have 0.02, 0.05, and 0.1. Relative frequencies can be useful for comparisons. Although it can be easy to look at the frequencies to get an idea of the distribution of the numbers for one group, if you have two groups, that can be difficult. For example, here we have years in school for males versus years in school for females, listing what year in school they are. So one represents they're in their first year of school. If we look at the female frequency, we've got 55 females in their first year of school, as opposed to only 25 males in their first year of school. So it may look like there's a higher percentage of females in their first year of school than there are males. But, in fact, that is not the case, because although the frequency of 55 is higher than the frequency of 25, there were also more females in the study than there were males. So when you look at the relative frequencies, you can see that 20% of the male customers were in their first year, whereas only 8% of the females customers were in their first year. So looking at the relative frequencies can be more useful than looking at the frequencies for comparison purposes. We can see, as mentioned before, there's a higher percentage of males in their lower number of years of school. And if we look at the female customers, we can see that there is a higher percentage of female customers in higher years of school. Another additional term of use is classes. Classes divide quantitative data into ordered sections or groups. Classes should have the following properties. For example, the classes should not overlap, A set of classes should include all the possible data values. The distance between the lowest possible value and the highest possible value in each class should be equal for all classes. Now let's look at statistical graphics. In this section, I will demonstrate several different types of graphics. In most cases, a specific data type has to be used for each graph. First, we look at a dot plot. A dot plot is a graph that has a dot for each observation in the data. So this stack of dots represents several individuals in our study. Now, a dot plot works very well for a smaller number of observations. In fact, it can even be sketched by hand. If you have a piece of paper, it is not too difficult to draw in a number of dots. But a dot plot does not work well when you have more than 1,000 observations, because as you can imagine, that stack of dots is going to get very, very tall. And either you have to scrunch them all down so that it's difficult to see how many dots there really are in that stack, or you have to use very tall paper. A dot plot can be used to show the distribution of data. For example, if we look at this dot plot, which represents the distribution of the years in school for the male customers, then we can see that there were a higher number of male customers in the lower years in school, and that the highest frequency was observed for 3 years in school. In a dot plot of continuous data, some of the points may appear off-centered, and so they're stacked where they would appear, but for example, you may have a dot at point 70, and at point 71 you may have another dot, but if you have a point at 70 and a half, that may have to fit somewhere in between those other two dots. And so rather than putting a point at each specific data value, in some cases they will be stacked. This is a good place to give a demonstration of StatCrunch and how we might create a graph in that statistical program. So here we have Stat 101 Fall 2011 final grades. If we go over to statcrunch.com, we can see the final grades data here in the spreadsheet type interface. So what we want to do to create a graphic in this program is go to the graphics menu, choose the graphic that we're going to create, in this case a dot plot, click Next so that we can determine if we want any additional information used for our graph, and then select Create Graph. Here is our dot plot. Now what we can do in StatCrunch is we can change how that appears. We can shrink that down a little bit if it looks like it would be easier to read. And then here we can see all of the data points because each one is represented by a dot. And we can look at the pattern of the distribution based on how those dots appear. You also have the options here to edit the graph, export it, copy it, print it, or just simply close it. Now if you select Copy, that will allow you to then paste the graph into a report that you may have created in Microsoft Word or some other program. A stem plot is another basic graph. It too should only be used if you have 100 or fewer observations. There are several different aspects of a stem plot. There's the stem, which is a list of the ordered roots of the numbers. So for example, right here, that first column of numbers is our stem, followed by leaves, which are the extensions to the roots that make up the completed number. So here we have a list of our leaves. We also include a legend which deciphers the stem and the leaves. So for example, we have our key right here. That's our legend. And essentially it tells us that a 5:1 represents the number 51. So if we go down here, we can see a 5:1. That represents a 51. That tells us that the tens value is here as a stem, and the ones value is here as represented as a leaf. So together, the tens value and the ones value gives us our 51, which is the data value that is being represented in this particular part of our stem plot. So from that we can deduce that the numbers in our distribution are 22, 45, 45, 46, 47, 51, 54, and 63. You'll notice that we have location here in the stem for a 30-something, but we don't have any leaves here, so we know that there were no observations that were in the 30s. But we still leave a place for it because that demonstrates that there were no values in the 30s. Whereas if part of the stem is missing, it changes the shape of the overall picture. So another thing is with these leaves, essentially we list them in increasing order out from the stem. So here we have a 4 and a 5 to represent the 45, and then we have 45 right next to it, so we have a duplicate there. We list every single observation in our data set, and we list them outward from smallest to largest. So the longer the branch, so to speak, the more numbers that are in that list. So what we can see from this longer branch right here in the 40s is that we have more observations that were in the 40s than in any of the other 10s. So the stem plot as well is used to show distribution of data. Here are some more examples of how you could create some more complex stem plots. For example, in this first set of data right here, we have 1, 2, 2, 3, and 5. We don't have any 10s like we did in the previous one. So in this case, how do we represent all of these ones values? How do we split those up into stems and leaves? Well, here's one thing that you can do. You can list all of the individual numbers as part of the stem, and then for leaves, have zeros. And so here we have a 1 and a 0. Here we have a 2 and a 0. And so this first one, looking at our key, it says that 1:0 represents the number 1. So we know that in our data we have a 1, and then here we have a 2, but we have 2 zeros there, so we know that we have actually 2 number 2s in our data. Then we have a number 3 and a number 5, which that does match up with what we have here above. This next example looks at what we do with decimal values. So here we have a key that says 2:3 represents the number 0.23. So if we look down here at our stem plot, we find our 2:3. We know that that represents 0.23, and so we deduce from that that the number on the left side, which is in the stem, is the representation of what's in the tenths column, and the number that's represented by the leaf is in the hundredths column. So this number right here would be 0.10, and this number right here, well, the first one we would have 0.44 followed by 0.45. Okay, and so that matches up with what numbers we have up here. So these data are represented in this stem plot. In this third example, we look at what you do when you have more than just 2 numbers. How do you separate those when you're going to have gaps in a stem plot? If we look at the key, it says 97:3 represents the number 973. What we want in our stem plot is that the last digit represent the leaves, if possible. And so what we've tried to do with each of these examples is have the last digit in the number be represented by the leaf. And so we have 9, 7, and 3 as the digits, and we want to put those together in such a way that the 3 is the leaf. And so here we have 97 as the stem and 3 is the leaf. And so we have here what's in the hundreds, what's in the tens, and what's in the ones. So hundreds, tens, and ones. And that's what makes up the number. So then we have a 973 here, and then with this 1 right here we have 981 and 985 and so forth. A couple of things that you'll see here. One, we've got 97 followed by 98 followed by 99. We want to make sure that we don't have any gaps in between the sections of our stem. We also want to make sure that every possible number would have a place where it would be represented. So there are a lot of different types of stem plots that you can come up with based on the numbers that you are trying to graph. Here we have 100 values that are to be represented in a stem plot. And because there are so many different values, it can be difficult to actually create that plot because we still have to have a leaf to represent every single number. Because we have so many numbers, we have to divide the stems up into two different segments. So the numbers in the 50s, for example, 52, 53, 54, and so forth, we have to divide them up into two different sections because otherwise our list of numbers is going to be too long to fit on our page. And so we can make it more concise by dividing up each 10 number interval into two different stem sections. So what I've done here is I've made it so that the separation is at 5. So 50 up through 54 will be represented in the first part of the stem, and 55 up through 59 will be represented in the second part of the stem. The same thing is done for the 60s and the 70s, 80s, and so forth. So from 60 up through 64, right here, and then 65 through 69 right there, 70 through 74, 75 through 79, and so forth. We don't need to include the second section for the 90s because we don't have any values there and because it's at the end of the stem plot. So we don't have to include anything below our last observation or above our first observation. But if we did have blanks in between, then we would have to include that. So for example, if we didn't have any numbers that were in the 70s, we would still need to include both of those 7s in our plot because we have numbers in the 60s and in the 80s. If we look at this stem plot, we get an idea as to the shape of the distribution or pattern of our data. We have many numbers in between the 60s and the 70s, and we have fewer outside of that in the 80s and 90s and in the 50s. And it's very easy to see that at a glance looking at this stem plot. Imagine if you had a stem plot of, say, 1,000 values, you'd have a very, very cluttered stem plot that would be very, very large and would possibly not fit on a page. So what do we do if we have 1,000 values? What do we do if we need to plot 1,000 values and we want to look at a distribution like the stem plot? Well, what we can do is create a histogram. A histogram is a graph of a single quantitative variable. It has a similar appearance to a dot plot and actually a similar appearance to a stem plot. It can represent any number of observations, so whether you have 10 observations or you have 1,000 observations, you can represent them using a histogram. In this case, each of these bars represents one of our classes. Those that have 1 year in school in the first bar, 2 years in school represented by the second bar, 3 years in school by the third bar, and so forth. We have a graph here for the males and then a graph here for the females. But one thing you'll notice is that the scales are not the same. So here we go up to 140 for the females, and here we only go up to a frequency of 40 in the males, because there are fewer males than there are females in the study to begin with. And so it's a little difficult to make an appropriate comparison using unequal scales. So we can get a more accurate representation using relative frequencies. Because when we use relative frequencies, it's like we're using percentages. So here we have 35% or 0.35, and here we have 0.35. So we're using them on the same scales. Although, because this females came down from the title here and males did not, it kind of scrunched down our graph, but they're still on the same scale, so they can be compared side by side. So now we can look at the graphs and say, well, let's look at the distribution of males. It seems to start up high and then go down. Distribution of females is more level, but it increases more at the end, at the higher values, than it did at the lower values, like with the males. And that's something we observed looking at the relative frequency distributions earlier. A bar chart is a graph of one categorical variable. The different bars represent different categories. The height of the bar represents the frequency of that category. Because favorite color is a nominal variable, the order of the bars is not significant. So we have red, then green, but you could have easily included green and then red. And so you can't look at a pattern on a bar chart of a nominal variable and get a sense as to an overall distribution. Because each time you reorder the categories, you're going to get a different shape to your distribution. But it is helpful at seeing which of the categories have the highest frequency and which ones have the lowest frequencies. A Pareto chart is a type of a bar graph, but what we've done is we've ordered the bars from the highest frequency to the lowest frequency. And the reason for doing that is that it makes it easier for us to see the differences in the heights. Especially with bars like the green and the black, where they look like they're about the same heights, if they're on two different ends of the graph, it may be difficult to determine which one has the higher frequency. But putting them side by side and ordering them from highest frequency to lowest frequency, it is easy to see that the green bar is a little bit higher than the black bar. Even if we can't see that, we know that because of the order it's in, that the green bar had a higher frequency than the black bar did. Now we look at a pie chart. A pie chart is a pie-shaped graph of one categorical variable. The slices correspond to the classes. The size of the slice is proportional to the magnitude or the frequency of the displayed variable. It can be difficult to read a pie chart when you've got more than 5 slices, because the more slices you try to fit on that pie, the smaller those slices are going to be, and the more similar in size they're going to be, and harder to distinguish one size from the next. The slices are often labeled for clarity. If you look at the two graphs below, the colored graph is fairly straightforward to read and interpret. But think about those individuals who are colorblind, or think of what happens when an individual wants to make a black and white photocopy of that color pie chart. Now all of a sudden, if we look at this black and white pie chart, you can see we have different shades of gray, and it's difficult to see what the difference is between those different shades. For example, the black looks very similar to the blue, the red looks fairly similar to the purple, and the yellow looks fairly similar to the pink. Imagine if these labels were not there, we would not be able to see which color was which. And so it's very important to have labels when using a pie chart. A line chart has time as the horizontal axis, and essentially you connect dots to represent trends. It has another quantitative variable on the vertical axis. Multiple lines may be used to represent levels of a third class variable. So in our example, we have cost of tuition for public and private schools over time. We have a red line representing the public schools and the blue line representing the private schools. And if you look at the timeline across the bottom, you can see that it goes from 1980s to 2005, and each of those lines shows how the tuition has changed over that time period. You can see that for the private schools, the tuition has been fairly level. For the public schools, tuition has raised dramatically. In fact, it looks like at 2005, the cost of tuition at private schools is relatively the same as it is for public schools. Notice that by connecting the dots, it makes it easier to see the trend or the pattern of the points over time. A scatter diagram is a graph of two numeric variables. In a scatter diagram, we don't connect the dots. Two important definitions. We have a dependent variable, which is assumed to be a function of another variable, and it is graphed on the vertical axis. The independent variable is assumed to have potential influence on the dependent variable, and it appears on the horizontal axis. So here we are looking at height based on age. We have height in inches as our vertical axis or our dependent variable, and we have age as our horizontal axis or our independent variable. And it is assumed that age has an effect on height. We look at a scatter diagram to look for a potential shape. And again, we're looking at perhaps some sort of a trend. And so if we look at this particular graph of points, we can see a straight line pattern that goes from the lower left to the upper right. And from that we can deduce that the higher the age, the higher the heights, which essentially just means that in this age range, older people are taller than younger people. A box plot is a graphical representation of a distribution of one numeric variable. Quartiles are numbers that divide the ordered data into quarters. So, for example, 25% of a set of data is below the first quartile. 50% of that same data are below the second quartile. The second quartile is also called the median. 75% of the data are below the third quartile, or Q3, and 100% of the data are below the fourth quartile, which is the maximum. Now you'll notice that although Q4 is the maximum, Q1 is not the minimum. Q1 is the 25th percentile, meaning that 25% of the data are below that Q1 value. So there isn't a quartile that represents the minimum. Now in this box plot that we have here below, we actually have two box plots in the same graph. So we've divided one of our variables, years in school, by gender. And so that gives us two separate box plots, one for females and one for males. Again, we're looking at the shape of the distribution. So on the box plot, we have different points of interest. We have the bottom part of the box, we have the part where the line is, and we have the top of the box. The bottom of the box is Q1, which is our first quartile, which means that 25% of our data are below Q1. The middle line is at Q2, which is the median, or the 50th percentile. This Q2 indicates that 50% of the data are below Q2. The top line represents Q3, or the 75th percentile, meaning that 75% of the data are below Q3, which means that we have another 25% of the data that are above Q3. So you can see how the box plot is created, how it's proportioned out based on these quartiles. You can see that the middle line here is not in exactly the middle of the box. Why is that? That's because there are more observations in the lower half of the box than there are in the upper half of the box. Looking at the box plot for females versus the box plot for males, you can see the difference between the two distributions. Recall that for males, there were fewer individuals at the higher grades and more individuals at the lower grades, or years in school. With females, it was just the opposite. There were more females in the higher years in school and fewer in the lower years of school. And that is represented here by this box plot. And this is probably even an easier way of seeing that difference than when we looked at the two side-by-side histograms. In summary, tables and graphics are used to summarize data. Relative frequency distributions are typically easier to compare than frequency distributions. There is typically a specific variable type required for a given graph. So, for example, with our pie chart, we had categorical type variables. For our scatter diagram, we had not one, but two variables, and they were both quantitative variables. So each set of data that you want to graph are going to have a specific type of graph that will fit that particular type of data. And that is the end of Chapter 2, Tables and Graphic Displays of Data.